everybody. In this video, we're going to be talking about equivalent fractions. So when we're working with fractions, it's very common that you'll have multiple fractions that represent the exact same amount. For example, if you look at these region models of the fraction 1/2, 2/4, and 4/8, you can see that all of these fraction models represent the same amount. Like if these circles were pies or pizzas or something like that, the amount of pie or pizza that you would have in all of the situations is the same. And so these three fractions are equal to each other. And there's actually an infinite number of fractions that are equal to the fraction 1/2. Like for example, 3/6 or 50/100 or 25/50. Any number that represents the same amount as 1/2 is considered to be equal to 1/2. So in your book, there's a definition of equivalent fractions that says that if you can multiply the numerator and opposite denominator of the two fractions you're trying to see if they're equal, and if you multiply those and then multiply the other denominator and numerator, if those two products are equal to each other, then that means that the fractions are equal to each other. And this definition leads to Theorem 6.1, which basically says that if you have any fraction where you have your numerator and denominator, if you multiply the numerator and denominator by the same number, then that's going to give you a fraction that's equal to your original fraction. And the reason why this works this way is because let's say if I had the fraction 3/5 and I wanted to find an equivalent fraction that had a denominator of 15, well, I could multiply the top and the bottom of my fraction by 3. And the reason why this will create an equivalent fraction is because if I multiply the denominator by 3, that basically means that I'm tripling the number of pieces that my whole is split up into. So essentially, I'm splitting each of my 5 pieces up into 3 more pieces so that I have a total of 15 pieces. And when I do that, you can see that I would have to multiply my top or the numerator of my fraction by 3 as well, because these 3 pieces that I started off with are now 9 of the smaller pieces. And so that's what shows me that 3/5 equals 9/15. And you can also use this idea in reverse to reduce fractions. So if I look at 12/18, I can think about 12 as 6 times 2, and I can think about 18 as 6 times 3. And because this number and this number are the same, I can reduce this fraction to 2/3. So kind of the process that you think through when you're doing reducing is you are going to divide by factors that they have in common. And if you divide by the greatest common factor, that will reduce the fraction into simplest form. And so when you divide the top and the bottom by 6, in this case, what you're basically doing is you're saying, okay, well, I'm going to take my 18 pieces that are in my whole, and I'm going to split them up into groups of 6. So if I take these pieces and I split them up into groups of 6, you can see that's going to make a third there. Then if I continue doing this and splitting this up into groups of 6, basically that splits my whole up into thirds. And my 12 little pieces that used to be shaded are now 2 of the big pieces. And so this is why we divide the top and the bottom of the fractions by the same number whenever we're reducing fractions. And also, you don't necessarily have to divide by the greatest common factor when you're reducing. You can reduce in multiple steps. Like, for example, if I had taken 12/18 and I'd realized, oh, well, I can divide both of those numbers by the number 2. If I divide the top and the bottom by the number 2, this gives me 6/9. And that's basically because if I split them up into groups of 2, like this, this might take a little minute. There we go. So if I divide them all up into groups of 2, you can see that I now have 9 pieces in my circle, and 6 of them are shaded. But 6 and 9 are both divisible by 3, so I could reduce this further by dividing the top and the bottom by 3, which would give me 2/3. And that's basically taking these green pieces and combining them together into groups of 3. And so it would look kind of like this. And once again, you can see that 12/18 equals 2/3. So this fraction 2/3 is what we call the simplest form of the fraction 12/18. So there's an infinite number of fractions that are equal to 2/3, but 2/3 is the simplest form of all of those fractions. And the way that you know that it's in simplest form is if these two numbers are relatively prime, meaning that they don't have any factors in common besides the number 1. And you can also use the idea of equivalent fractions to help you solve fraction word problems. So, for example, it says, in Mrs. Smith's class, 2/3 of the students are wearing red. If there are 36 students in her class, how many are wearing red? So, in this problem, we have the fact that 2/3 of the students are wearing red, which means if you had a total of 3 students, 2 of them would be wearing red. However, there's not just 3 students, there's actually a total of 36 students. And so if you wanted to solve this problem, you would basically be asking, well, what fraction with a denominator of 36 is equal to 2/3? And in this case, it's not too hard to solve because we know that 3 times 12 equals 36. And if I multiply the top by 12 as well, that will give me the number 24. And so out of the 36 students total, 24 of them would be wearing red. So that's how you would use equivalent fractions to solve fraction word problems. And we also talked about why you multiply the top and the bottom by the same thing, or divide the top and bottom by the same thing if you're reducing fractions. So if you have any questions, let me know, and I hope you guys have a great day.